Record. Okay, so we are recording now. Right. All right, so now let's open up Scholar. All right, so I'm gonna get a job here. You. Just gonna give it a minute. All right, there we go. We're gonna create a new Jupyter here. We're gonna do these examples with MNIST, but for the project, you guys will generate color images. Okay, so conditional color images. So that's basically what I'm asking you to do. All right, so I'm going to click on new Python. All right. And we're just going to call this so just GAN, regular GAN, MNIST GAN actually. MNIST GAN. All right. Okay, so a couple of materials for you guys to take a look at and use as reference. So you can go to my GitHub, right? And under deep learning algorithms, you can click on that and then click second edition here. And then it's chapter 8, GANs. And you can click on this Jupyter. This is the one that we're going to do today. Okay, so all the code is there. And we're just going to go through it. This just generates random MNIST images. Okay, and I'll describe the code basically. Then also, I have some notes. So if you click on this deep learning and then chapter 8, Generative Adversarial Networks, I got some notes here so you can read through that as well. So this is basically where you should begin your journey here. But at some point, we'll jump into just papers, okay? Because I have a nice tutorial, like a nice tutorial I found online on like diffusion models and everything. So I'll give that to you and you'll have to read that, okay? Because we're getting Sora. I don't believe there's a paper because Sora just came out and is OpenAI doesn't really tell us how they do things exactly. So, but we'll kind of explore it as a research idea. Does that make sense? But basically, the whole thing is we want to generate. I think Sora also generates video, so we're not going to be at that level. But we just want to generate images. It'd be nice if we could like enter some text and embed that in, but I think that's pretty different. So I'm not asking so much as that, although I encourage you guys to try to do something like that. Okay, but as long as you can do a nicer conditional example than the one I'm doing, should be fine. Any questions? And that's your mini project, their last mini project. Presentations will be the week before finals. That's it. Got it? All right, so you definitely should start working through that. All right, so let's take a look at GANs. So GANs are generative adversarial networks. Here's the basic diagram that you always see related to GANs. Basically, you have two neural networks. Right? You have a neural network that is called a generator, and then you have a neural network that is called a discriminator. And they're playing a game against each other. So the analogy that everyone uses is the forger and the detective, right? So like think of art. So you got a forger trying to make Picassos or Rembrandts or something like that. And then you have the detective who's trying to spot a fake Picasso from a real Picasso, right? So they're playing against a game against each other. The generator makes a painting that goes to the discriminator who says real or fake. Do you guys see that? And basically the idea is that the generator becomes really good and the discriminator becomes really good. So by both of them becoming really good, you really end up with a really good generator, because the generator every time has to fool the discriminator, and so it needs to become even better at forging. Does that make sense? So that's the idea usually of GAN models. So these were proposed by Goodfellow in 2014. You can look at the paper. There's another guy, forget his name. It's got a long name, but apparently he also proposed it like in the 90s, but the current version as is the one proposed by Goodfellow 2014. Okay, so that's kind of the idea. All right, so the discriminator is actually pretty straightforward. It's just a normal classifier as you guys know it. It's got the input as the image and the output is just true or false. That's it. So a logit basically indicating that. And then the generator takes in an input, which is usually a random vector of data, just noise, and then it should produce something like an image. So in this case, for instance, if we're making images, then let's say we're using MNIST, so the input could be something like a vector of size 100, and the output could be something like a matrix of size 28 by 28. In our example, we're just going to spaghettify it, so it's going to be a vector of 784 that we can reshape. And that same thing is the input to the discriminator. So an image 28 by 28 spaghettified into 784. All right, and then once that goes in, it says true or false. So the key thing to understand is that real images also go into the discriminator. Do you see that? So here you have the real data. So, the actual MNIST data. So that goes in, and should be a true when you're classifying, right? And then the generator produces images from random things, and that the associated label depends on the objective. So for the discriminator, if you're training the weights of the discriminator, that image should be false. Do you see that? But there's also another step where you train the generator, and when you train the generator, the label associated with that is true, because you're trying to fool the discriminator. So the loss function is calculated in terms of the discriminator, and there is basically essentially no loss for the generator, because the generator uses the discriminator's loss. And that's kind of it. That's the idea of it. You can see here, the input to the generator here is just random data. When we do the conditional, we will append a little vector to the random data to indicate the condition so that it associates those labels with the image that comes out here. But that's basically how it works, okay? So you can take a look. Any questions about that? All right, so we'll do, of course, the code today. We'll go over this and build this from scratch. You can read through it. Those are my notes on it. Basically, it is based on autoencoders in a sense, and you can make them as complex as you want. So our generator and discriminator will be very simple, but you could add a CNN to it, because you're processing images, etc. So that any architecture that you can think of can be in there. Okay, and so we'll go over this code today and kind of try to generate our images. I'll talk about these objectives, and we'll try to generate some images such as these, which, as you can see, this kind of looks like a 5, right? And then the next step will be to talk about conditional GANs. So you can see here I have a graph of the conditional GAN, and if you look, it's very similar to the previous one. Have the generator generates an image that goes into the discriminator, but also the real images will go into this discriminator. The only difference really is that in the regular GAN, you only had this blue vector called noise, in the conditional GAN, you have the blue vector called noise, but you also have another vector called condition. So if to make this, to relate this to, for instance, to MNIST, that would be a vector of size 10, where you would say, oh, this is a 3, this is a 7, a one-hot encoded vector, and that's it. So pretty simple, and we'll do this trick. If time permits, we'll hopefully also do the conditional GAN today. And you should be able to see that if I say I want a 7, it'll generate 7s. If I say I want a 5, it'll generate 5s, and so on. Okay? All right, so let's go ahead and get started. So we've got so those are the notes. You can read through it. I showed you the link where it is, right? So if you want to read stuff and more detail, and the code, as I said, is here. So this is the code that I'll be implementing. All right, so let's go ahead and get started. All right, so just add some here. And like I said, you can follow along on this one, given that you don't really need a GPU. It should train fast. I think it works for the multi-layer perceptron, but you can also try other, architectures, etc. All right, so a simple GAN to generate images. So let's go ahead and load the libraries. Okay, so Torch, we're using Torch Vision, Matplot, and Pill since we're dealing with images. See if we've got everything here. Okay, so that worked. Let's go ahead and add some more libraries here. Sklearn mainly, MXL, MLX10. Okay, so that worked also. And Torch libraries. All right, so everything good. So no errors, thankfully. Okay. All right, so some of the parameters here. We're going to be using data sets. So here, I'm not going to be reading the data from a folder. I think I did this already for one of the examples with Sci-Fi, right? We read the actual images, so I've already shown you guys how to do that. And you will need to do that for your mini project, right? So I'm assuming you'll download some images off the internet, something. So you'll need to take those images and convert them into tensors, Torch tensors. But in my example here, I'm just using data sets to get MNIST. All right, so let's add some of the parameters. Parameters. Okay, so it's a neural net, so it's going to be the basic things. Got the learning rate. The batch size is 32. The N epochs for now 30, but you can increment that. Okay. All right, so now we're going to read in the data. All right, so let's download. Okay, so we're going to download this folder. I may need to create datasets MNIST. You know what? I'm just going to do this. All right, datasets MNIST, data path. And this is going to be the train set. So download it. Okay. Not seeing any errors. Okay, good. Let's take a look at this one over here. So I'm going to data seconds ago. Okay, good. So no issues. Okay. So now let's do the same for the test set. So that's MNIST train and then MNIST test. Okay. Okay, no issues. Okay. All right, so now we're just going to convert these into Torch data. Okay, so here we're going to use data set MNIST, the data path, train, and then a transform basically that just converts the images into Torch tensors. Okay, any questions? All right, and this will create MNIST train and MNIST test, basically. Okay, so no issues there. Let me add a few cells here. All right, so we have our data. Now, let's verify that we do have, in fact, some data in there. So print an image, maybe. The images. So we're going to grab from MNIST test TR data 333, convert it to NumPy, and used image, basically. So, all right, there it is. So we got a 5. So as you can see, we do have the data, and that's a good thing. All right. Now, for this one, we don't need transfer learning. It works perfectly fine from scratch. But of course, as you guys start doing your own things, transfer learning may be needed. There are some transfer learning GAN-related things in FastAI. So FastAI does have a few things. All right, let's take a look at the data shape just to have a sense of how it works, what it looks like. So MNIST train TR data shape. And we know that we've got a tensor, 60,000 by 28 by 2028. Remember, this is grayscale. So one issue with this code, if you use it for color images, is that you're going to have to modify some aspects of it, right? The shapes, etc. Because so definitely that's a requirement for the homework assignment, is that you should do color images, not black and white. Okay, please. All right, and everyone should do different data sets, etc. All right, so now we have that. We know that. Now, as usual, we want to create the data loaders. All right, so I like using data loaders. So let's go ahead and create those. I'm just gonna add here. Create data loader. Markdown 1. All right. Let's save this one. All right, so now let's go over here. So I already printed this shape, so I can print the test shape just to kind of get a feel for that as well. So that should be 10,000. So this is 10,000 by 28, 10,000, 28 by 28, basically. Okay, so I'm gonna hit save. All right, now we are going to create the data loaders. Okay. All right, so here we have a data loader for train and a data loader for test. So the nice thing about using this function is that basically we already have the data in the format that the data loader needs. Usually data loaders like a list of tuples, right? Where you have the torch image and the associated label as an index, as an integer, basically. Does that make sense? So we usually a list of tuples. All right, so that's already an MNIST train, MNIST test. So that's already, the data loader will be able to handle this as we have it, which is a torch tensor. MNIST train TR. We don't need also, I'm trying to think here. We don't need the labels here, right? So we're used to having MNIST where we have an image and a label 7 and a 3, but because we're not doing conditional, right? We don't need the labels. In fact, we're gonna, this is actually maybe not be intuitive, but the GAN, we have another set of labels. And basically the labels are, we're gonna say if that image is real or fake. Okay, because remember, all that we're trying to generate right now is random MNIST images. So you can think of it as we're trying to figure out the distribution of the images, and then just from there, we're going to generate, you know, things that have this, think of it as the mean and standard deviation of that distribution, right? With some noise. So that's kind of how you should approach this. So the labels that we're going to use are just real or fake. So depending on our goal. But here we create, and the batch size, I think we said it was 64, basically. Okay, so let's go ahead and create our train data loaders. So that's done. All right, good. So now, that's really the easy part. Now comes a little bit of the hard part. I have a few helper functions here that we're going to be using. So now we're going to have two losses, if you will. We're going to have the loss of the GAN associated with the GAN and the loss associated with the discriminator. All right. And the objective of those is actually for them to kind of meet at some point. We don't want the losses of the GAN to be too good because then the losses of the discriminator could be really bad. Do you see that? So it's kind of like this optimization of these two losses, but we should be able to see it in a second. So this is this function here. I've used this convention of calling it real, fake, and tricked, right? So we'll use that as well. So let me add these utility functions, and then we can talk about it. Markdown, utility function. Add a few more cells in here. Okay. All right, save it. So this is going to be a function for plotting the losses. I'll describe it when we need to. Okay. I also have some performance metrics in here. This is the familiar function I always use for classification. So I'll throw that in there. And then I do have some functions that we are going to need. This is for plotting the metric over the epochs. But these two in particular are going to be very useful for generating the noise that goes into the GAN. So this is a concept that might be very confusing or weird, right? But neural networks need an input, right? Neural networks need an input and then they produce an output. So interestingly enough, with the GAN, you just provide random data. Like pick a size, put some random data in there, and eventually the weights will go from the random vector to produce something that makes sense. So it's a type of a transformation all through the weights. Does that make sense? Yeah. Questions? Yeah. So imagine, like, remember old TVs after 11 o'clock, they had like that noisy screen. Think of it that way. And then out of that comes the picture. So that's kind of a good analogy. All right. So we'll take a look at some of that. All right, so let's add this function also for plotting the metric per epoch. Okay, so let's add that in here. Okay. And then we need, I have two functions in here. Random G vector input. random G vector input. So if you notice, they're basically the same function, except one is for batches and the other one is not for batches. Why do we need that? Because if we're training with batches, we need to, for every sample in the batch, we need to provide a noise. So that's all it does, okay? But they're basically the same thing. So I'm going to copy both, and we can kind of describe them a little bit more. But let me just copy them in there. I think those are all the utility functions. You can see the neural net architectures are coming up next. All right, so if you notice, let me actually, I don't know if I added these in. Okay, so if you notice, all that happens here, you invoke Torch, and then you tell it that you want a random vector of size 100. So that's going to be the input to the GAN, and that's return. And over here, you say the same thing, that you want a random vector, but this is going to be batch size by 100. So I think our batch size was 64, so it would be 64 by 100. It's kind of a matrix, and each one of those will serve as the noise input to the GAN for training. So this is useful because maybe in the training we need this one, but once we're doing inference, if we just want to generate one image, we just use this one, okay? And, you know, there are other ways of doing this, but this is just what I want, you know, kind of ended up doing. All right, so we've got that. Now we can start looking at the network architectures. So in this, so I'll add this title. All right, so let's do Markdown. All right, so in this example, I think I have two architectures. I have a DLNet. You can see it's a deep learning with two hidden layers. No, sorry, this is not. I have a generator net and a generator DLNet. I think, if I remember correctly, what is this actually? 4. I just used this as reference. You can see by the shapes it doesn't relate to the GAN. So this one actually does. This is the generator net, and this is a generator DL net. So the difference should be what? 100 to 256, 256 to 784. What type of a neural network is that? Just a simple MLP, right? So it's got one input layer, one hidden layer, one output layer. You can see that, that's it. It's pretty straightforward. Why 100? That's what I picked. For MNIST, that works fine. Maybe for your color images, you need something else, right? That might be a parameter to tweak, read about. But anyway, so we generate that random vector from the other function that I showed you. The hidden layer has 256. And then the output of it is 784, which by now you should know that's the spaghettified version of the MNIST 28 by 28 images. And so that's it. This worked, so I just stopped there. I did create the DLNet architecture. When I did this, I'm pretty sure I wasn't using a GPU. And so I wasn't able to learn enough. Didn't work very well, but maybe with better architecture, but better things, and more time, it might actually produce crisper images. I'm not sure. Okay, so it's definitely something to try. When you guys do this, you can add transfer learning in here, right? You could make a CNN in here, all kinds of things. So it's entirely, you can play with the architecture. Because MNIST will work, but you're doing a mini project of, you may decide that you want to generate cats or dogs or something. That may be a much more difficult challenge. Does that make sense? All right. Okay, so so I can skip this one here, but let's start with the MLP one. So I'm going to copy that one into my architecture here. And we can describe it basically as you're familiar with this already. So it's a class inheritance, right? And then module is being inherited. This initializes the inherited module and then module. And then we have our architecture here, basically. So, and in linear, 100 to 256, I'm using a leaky ReLU, right? Which is like ReLU, okay? That's the activation function 1. Then layer norm is happening, right? That needs to happen on the hidden layer, right? That comes out. So basically, it's like batch normalization or layer normalization is this idea that you don't just normalize the inputs, right? Now you also want to normalize everything that's coming out of a hidden layer. Neural networks just learn, better by doing that. Okay, so it's just a standard approach. Then we have a linear from 256 to 784, right? That goes from the hidden layer to the output layer. Notice here it's sigmoid, and notice interestingly, yeah, so this is the values. This is the actual image that's being generated. Does that make sense? And then there's a dropout basically as well. Okay, so those are the things that we're going to be using. Now let's look at the architecture. So I don't use everything. As you can see, you can play with the dropout, but I didn't need to use it. So the random vector comes in here. Rand input goes into linear, that produces X. X goes into activation 1, which is the leaky ReLU. That then goes into norm 1, which is this layer normalization. And then that goes into linear 2, which is the 256 to 784. And then the final activation 2 is a sigmoid, basically. Sigmoid should do 0 to 1, correct? All right. And then and I didn't use dropout. So, but you can tweak it. All right. And then that X I rename it YPred, and boom, I have a thing that generates images. So we can use this, if we give it random data, it'll generate images. It'll probably be random images, but it'll generate images. Okay. So let's go ahead and do that. I'll add the DLNet just, kind of to add it, but like I said, I wasn't able to get this one to generate good images, but I'll provide it to you as an example in case you want to take that. So this one's similar. Input vector is 100, and then it goes to the next. It's got 2 hidden layers, right? One that is 60, and then the other one is 120. And then again, you get 784 basically. Okay. So you can see here, I show basically how you can use these. So got the linear, the activation, the norm, there's dropout, linear 2 activation, norm, dropout, and then linear 3 and the activation. Okay, so you can play with that architecture. All right, so now let's go back here. Now there are 2 architectures, right? And again, so one is the generator, and the other one is the discriminator. The discriminator takes images and produces an output, which should be a label, true or false. This is like the basic classifier that you've learned before. There's nothing fancy going on. So let's take a look. All right, so here we have discriminator net. So let's take a look. So what is the input? 784, the spaghettified image, right? And then this discriminator has 2 hidden layers, as you can see. So it's got one that's 100 and one that's 50. And notice that the output is just 1 neuron because it's a binary type of a classifier. Make sense? Pretty easy, right? So a lot of the GAN is actually very straightforward. It's really in the training that it gets a little bit like, but everything else should be okay. All right, so here, same description. Let me load this. Okay. Same description. The X input goes in, that's the image, goes through linear 1, then goes through activation 1, which is a standard ReLU. Then that goes into there's dropout included. Then it goes into the next linear, which is this one, next hidden layer. That one also has its activation, which is ReLU. There's a dropout in there, then linear 3, which is from 50 to 1. And that goes into the activation 3, which is a sigmoid. And that makes sense because there's only 1 neuron and the output is 0 or 1. Right? Which should be the label, basically. Any questions? Pretty easy, right? All right. All right, so now we have the GAN architectures defined. And now comes the training function. As you can see, this is really where it's a little bit confusing. Then the core functions, you start the training process, and then basically you start generating. So as you can see, most of the heavy lifting or the complicated aspects happen here, okay, in the training function. So this is, I've tried to make this as simple as I thought it was, intuitive. Some people do this a little bit differently, but you know, let's see if it makes sense. All right, so let's go ahead and start defining our training function here. Okay, so training function. Markdown, run. Okay, now I'm just going to copy that in. Copy. All right, so let's go through this one, right? So here I have this concept of collecting the three losses: the losses of real, the losses of fake, and the losses of tricked. So the losses of real are when the image is real and the label, you know, like it's a real image and it should be labeled as a real, right? For the discriminator, when we're so you have to think of think of it of the point of view. Who is being trained here? The discriminator or the generator? Because remember, the discriminator has weights, the generator has weights. They both have separate weights, right? So for the discriminator, if we're doing losses real, then basically we're training with the real MNIST data, and that should be marked as a real. Do you guys see that? Fake would be what? When the discriminator gets a fake generated image and labels it as such, right? So from the point of view of the discriminator. But tricked is that you fooled the discriminator. So that means the generator generated an image, but instead of marking it as a 0, it gets marked as a 1, real. You see that? So that's the whole thing. So real image, real. Then 2 fake images, right? But one is real, one is fake, the other one is real. It's fake for the discriminator, is real for the generator when we're updating the weights. Because really it's like, if the generator generates this image and it fools the discriminator into saying it's 1, then that's a good set of weights. If it doesn't fool it, then it's a bad set of weights, okay? So that's basically what is going to happen. So we keep track of 3 losses so that we can plot them as well. All right, so let me just run this one. It's not going to run, but all right. So now here, this is broken down into the 3 things. So you have the training loop function, number of epochs. Notice here that it takes gmodel, dmodel, dlossfn, gopt, and dopt. So basically, there's the model for the discriminator, there's the model for the generator, right? The 2 neural nets. Then we have only one loss function. Do you guys see this? There is no generator loss function because everything is updated based on the discriminator loss, since that's the thing that we're trying to fool. Yeah, so there's only one. However, there are 2 here ops, gopt and dopt, because we do need to modify independently the weights of the generator and the weights of the discriminator. So these are the optimizers, if that makes sense. All right, so we need to modify them separately. All right, so we pass those parameters. Notice over here we have the classic 2 for loops, so for epoch and range and epochs. And then we have the reading the batch from the train set, XB and YB from the data loader. So this should be a batch by 1 by 28 by 28. Remember that PyTorch likes to have this to be the channel. So when you do this in color, that would probably need to be a 3, right? And then the batch here is 64. So now this, of course, then will need some processing because we have when we get an image and it goes into the discriminator, right, it's going to need to be spaghettified, basically. So that's this reshape operation here, right? So we're taking basically these three, 1, 28, and 28, and making it into 784. And the -1 should just give us the 64 of the batch size. Does that make sense, guys? So this is just a standard reshape. This could also be a view, but we're taking a tensor that looks like this, right? 64 by 1 by 28 by 28, and converting it into a tensor that is 64 by 784. Got it? All right. We have a squeeze operation here, XB also. So this squeeze, I think it's because, well, we can print it, but I'm pretty sure it has to do with like when you have 784 and you want to make it 1, 784. All right, so it's torch squeeze. We take XB, dim1. Dim1 would be here, maybe. I'll print this when I run this. So let me actually do that, because I'm curious now. I'm going to put an input here. I can't remember exactly. So let's add the code that we need so we can look at that shape. All right, so we're going to need, and then I'll come back and explain all these things. So let's just copy all this. That should give us the shape. All right, so I'm going to put that here. Right, so we're going to instantiate the generator, the discriminator. The lost is the type of a cross entropy, BCE lost, I think. And then here we have the 2 optums, and we're going to run it. So let's just actually print this one. I'm curious to know. So I'm going to do print xb.shape. And after, I'm going to do print xb.shape. All right, so we should be able to see what the squeezing is doing there. It's obviously doing something. All right. Okay, there we go. So I'm getting rid of the 1 in there, which if I do the -1, it should also take care of it, right? All right, anyway, that's what it's doing. It's just getting rid of that one. So see, that's why that's useful. All right, so I get rid of this, and then because it's not really relevant. Any questions? Make sense? Perfect. All right, so now I'm gonna kill this. All right, so we can go back. So we can get rid of this print statement. I'm seeing what it does. Get rid of that print statement. And then pretty sure this one will just make the images. Do I still have that? 32 by 784, right? That view thing or reshape -1. All right, so then the images are perfectly shaped, the tensors, to go into the model. Okay. So now let's take a look at, actually, let's define a lot of these parameters. So let's jump down here to the core, invoking the core functions. And then we can go back to the training function, given that that's the most complicated part of this whole thing. So call the core functions. It's going to be so tough. All right, so pretty much here, we instantiate the generator, right? Here, we instantiate the discriminator. So both of those things, done. The loss function for dloss_fn is just BCE loss. You can look this up, but I think it's the binary cross entropy. Yeah, there you go. So binary cross entropy. And so basically, we're just doing a classifier of 0 or 1, true or false. So very, very straightforward. Notice this is really important. I really like this approach of coding a GAN. So I think you can code it in other ways. But if you notice, we invoke torch optim atom, the atom optimizer, and twice. One, we call it GOpt, and the other one DOpt. And the idea is that we are tying the model's parameters here. So you see how we're tying the G model. So basically the weights of the generator here. And then in this one, we are tying D model parameters. So basically the weights of the discriminator. So now we can update, you know, when we see, like we trick the discriminator, you know, then, you know, we update the weights of the generator, basically, right? So we're going to be playing that game. The learning rate is the same, but this is really the important part. And then after that, we just invoke the training function with all of these parameters and perform the training. Does that make sense? All right, so that should be hopefully straightforward. So now comes probably the hardest part of this. Okay, so now we've done this, and let's just break this into the sections. So there's this section, and if you notice, this section should be only for the discriminator. You see that? So I've even wrote down here, no G training, and then down here, yes G training. So what that means is that as the code comes, as the data comes through here, it's like you are not going to train the generator weights, okay, during this phase. When you come out of this, then now you start this section over here. Notice no discriminator training, only generator training, okay? So basically, that's what's going on. So let's take a look. So for the discriminator, we go in here, right? And what do? We invoke the G model, right? G model. We give it a random G batch vector input, so a noise, the noise vectors that go into the generator. And we have to detach. So this is just like a technical thing that has to happen in the from the graph. And then that generates an image. The generator now generates an image. Okay. So here, there's two things. Train the discriminator with real data, which would be the real images, and then train discriminator with fake data, which is the images generated by the generator. Okay. And really what matters there is the label that we give it. Okay. The label that it's going to say real or fake. So here we can see train D with real data. Okay. So even though we have data here, a batch of generated images from the generator, we're not using that here. Instead, here we're using XB. What is XB? XB is the real set of MNIST images, okay? So that goes into those real images, go into the discriminator, and the discriminator is going to produce the real Y pres, okay? So these predictions, basically it should say that these are real images, right? So real images. So now that goes into the loss function, and the loss function is going to compare the predicted images to what? To just ones, basically. This doesn't come from YB over here. Do you see that? It has nothing to do with a image 7 being a 7 or a 3. In fact, it's just something that you're like entering directly yourself. So if you think about what this is doing, this is a torch once of size batch size. So think of it as a vector of what is the batch size? It's 32, right? So think of this as a vector of size 32 of all ones. Does that make sense? Where we designate that 1 is real. So basically we're saying this should have predicted, should learn to predict that when it sees real images, it should predict all ones because we're giving it that information here. That's real. Does that make sense? And that's the loss that we're going to try to minimize in this point. The fact that it should learn that when it sees real images, it should learn to predict that they are ones because they are real, because we give it that information. Okay? All right. So then once that's done, you know, the familiar functions that happen all the time, right? You know, we've got the loss calculation. So then notice here, what are we going to update? We update the weights of the discriminator. So that's why we're invoking dopt, because if you remember, dopt is this one, which is tied to only the weights of the model. Okay. All right, perfect. So here we are over here. So we zero out dopt. This is d-real loss. So we perform dot backward, which is calculating the gradients, and then dopt step. We update the weights of the discriminator. Got it? Based on that information. Now we repeat the same step, but now what are we going to give it? We're going to give the discriminator the fake data. Okay, so we give it the fake data here. So where's the fake data coming from? It's gen_img, which is coming out of the generator model, where the input was noise, basically. Okay, so gen_img goes into the same D model as before. And now I'm calling this dfake ypred. So here the discriminator, because it's looking at fake images, should learn to say what? 0. Very good. So it should learn. So it here is just predicting randomly, right? So it is up to us to define it in the loss function what it should learn. So we invoke .dlossfn, where we give it dfake ypred, right? That's there. And we say that we want to minimize the difference. And notice the key concept to understand is this one. What are we giving it there? Torch.zeros batch size 1. So effectively, that's a vector of size 32, right? 32 by 1 of what? Zeros. That's the trick. Amazing, right? It's like you become famous when you do little things like this. All right, so anyway, this made Ian Goodfellow famous. All right, so now you do this, right? You have your dfake loss. And so basically now, notice again, dopt. So dopt, remember, is what? Dopt over here is tied to the D model parameters, the weights of the discriminator. So once again, you're training for the discriminator. So you say dopt, the same 3 functions we always do. So we zero out the GANs, then we take in terms of dfake loss, we're going to perform the backward operation to calculate the gradients, and then boom, dopt step, similar to this one, update the weights, only of the discriminator. You got it? All right, now comes the last part. So if you're following along, you're almost done with GANs. Because if you understand this next concept, which is the thing that maybe is the most confusing, you understand them completely. Okay, so now let's think about this part. Now here, notice the comments. No detraining, and then yes, detraining here, but you're pretty much done. So what happens here is, once again, G model, right? G model. That's the GAN. Takes in random G batch vector input. Notice over here, random G vector input is the same thing, right? So plug that in, okay? What does it produce? A batch of fake images, right? 32 by 784. But now the GAN is, we're gonna update the weights of the GAN and not the discriminator. So these weights need to be updated, right? In terms of minimizing the loss that it should fool the discriminator. This GAN does not have its own loss. So here's the trick. Train G with D loss, you see? We need to trick D, the discriminator. We need to trick it. So we provide the gen_img, right? Just like we did over here. Similar idea. We provide the gen_img to D model. Same as here. But this now, I'm calling it D-tricked ypred instead of, because it's when you're tricking. So we invoke dlossfn. If you notice, dlossfn is the same as this one, same as that one. So we only have one loss function in terms of the discriminator. So we provide the predicted values, which initially they're just random. It doesn't, the weights are random, so it doesn't know what those weights are. But the trick is, if you notice, that it should learn based on what we say here. This is what determines everything. So when we generate fake images from the generator and we give those to the discriminator, what do we want the discriminator to say? I'll repeat this. I know it's a tough one, right? When we generate fake images, we're looking at this from the point of view of the generator. The generator wants to be really good at its job, right? So when we give the noise and the generator generates images, and we give those to the discriminator, what do we want the discriminator to say about those images? That they're real, exactly. We want to fool it. But really, in the previous step, we gave it images and we wanted the discriminator to say that they were fake because we were training the weights of the discriminator. Now we are training the weights of the generator. So when the generator generates images that go into discriminator, we want to fool it and we want, or trick it and have it say that they are real. You see that? That's the whole trick. If you think about it then, in the DLoS FN now, we provide torch ones batch size 1. What is that? It's effectively a vector of size 32 by 1 of all ones. And that's what we wanted to learn. So initially, remember, these are just, random stuff. They're bad values. But after doing the optimization over many epochs, we are updating the weights of the generator so that they become really good at generating images that go into the discriminator, and the discriminator says that they are ones. Got it, guys? Is that clear? That's the key concept, right? So notice another way of saying is, here we gave it ones, here we gave it zeros, here we give it ones again. But notice another thing, right? So we take the difference between the tricked and these ones to produce our de-tricked loss. Notice it's a different name from the other ones. Then now, notice this part is different. Before, we always said de-opt, right? Because we were going to update the weights of the discriminator. Now we say what? G-opt. So we zero out the gradients of G-opt. And now we do de-trick loss, which is this one over here, which is based on the difference, right? And we take the dot backward, calculates the derivatives, and then what do we update? G-opt.step. So before we were updating de-opt, but now we update the weights of the generator. That's it. Effectively, that's what we want. We want to always update the weights, right? So we're building a generator, right? We're changing the weights of it, and we want it to generate images that go into the discriminator, and the discriminator sees fake images but doesn't say 0, it says 1. That's it. Wrap your brain around that. All right. So anyway, so hopefully that you get that idea, but that's effectively all it is. And then after that here, this is just printing basically the losses. And if you notice, I am saving them in those lists that I created before so I can plot them, because actually there's something very insightful in this plot diagram, as we will see in a second. Okay. Any questions? All right, great. So I have this one over here. So that's the training function define. I've already defined my models and everything. So we can probably run it and do the training at this point. Yeah, so let's go ahead and train it. This will probably train really fast. Okay, there we go. And it's learning, I think. Okay, so there we have one. We just have to give it a minute there. Okay, another one. Okay. Now keep in mind, we have now various losses, right? And so we have to strike a balance. So it's almost like the losses should be the same for all, right? That's like the perfect balance. So I'm printing every iteration. So I think I did 20 iterations. 30? Okay. All right, so let's just wait. Yeah, let's just give it a minute. But yeah, this is kind of what you'll have to do for your mini project. Find a data set of images or whatever you want to generate, and it needs to be conditional. So in a sec, I will provide, after the break probably, the logic for conditional. We're going to build it up. And yeah, and then next week I'll probably cover like fast AI or something, transfer learning. We'll do the art style transfer as well, and just kind of like that. But you should be able to start working on your mini project with these scripts. All right. Did any of you run this already? And it runs? Do you know how long it takes? But it's a bit slow, even for a GPU. All right. So after, let's just, so it's going to print 30. So I guess I can talk about this while it's doing that. So basically, I have that function plot losses, plot GAN losses. So we're going to give it list losses real, list losses fake, list losses tricked. You can see they're plotted over there. I really like this graph because the green is the trick one, right? And then the real and fake are the ones related to the discriminator. So basically, these two are related to the discriminator. This last one is related to the generator. And that's really like the intuitive concept. So if you notice, these two kind of have this thing going on, and then the discriminator has this. So they're kind of like meeting, right? And this is what you want. If you are training your model and it's like one is, like you have these really low, sorry, but this really high, then the GAN didn't learn. You see that? And at the end of the day with a GAN, what you really care about is the GAN, right? So you're trying to generate. I mean, some use cases you might be trying to generate a discriminator, but for a generative model, we want the GAN to have a shape such as this one. It doesn't quite meet, but you narrow that down somehow. Okay. All right. And then, so we're going to so it's still training, but I'll generate this. And then after that, we just basically have a train GAN model. So we're just going to give it random data and, and then reshape it, basically convert it into a NumPy, and it should generate an image. So as you can see, that kind of looks like a 0. That looks like a better 0, I think. That looks like a 5 to me. I don't know what that is. 4 or a 9, maybe. A 5, right? And then this is just the maths. We can. This is how to generate. Initially, you can, when it, it's not trained, it'll just generate random noise, basically, of the right size. But yeah. All right, so that's kind of the idea. So it's kind of halfway there. I can't really do anything. Sorry. Do you guys have any questions? Does it make sense? Do you understand?
Train it more than 10 times because the graph got pretty good.
Do you want me to restart it and just run it for 10? I don't know, Joey. I just
well, I don't know. I know you can train a lot and still get better without showing on the graph.
I should have done 10. I mean, I could restart it again.
Oh, stop it now.
Stop it?
Things.
And just decrease it to 10?
Well, you can stop it and it should be fine. It'll remember the model.
Okay. All right. Great.
And if now, blame Grandpa.
Blame Dad. Hey, I'm just doing what you say. So All right, so let's see.
It gives a bunch of errors, but then if you just continue on, it'll, you know.
Yeah.
Perfect. All right, perfect. All right, so then let's do that. Let's plot the losses and see if we can generate some images. Yep. Yep. All right, so we are going to plot the losses. Let's see what we get. Let's see if we do get. I did 30 epochs here, so what you're saying is it should be there, right?
Yeah, but if they look at the Instructor,
Yeah.
so-
All right. No, that's a good, good observation. So let's try it. Okay, so we're gonna plot the losses. And yep, you can see that the losses at 10. It really didn't take that long for this one. Okay, so that's good. So I'm gonna save this. All right, so now it comes the moment of truth. Do we actually can generate good MNIST images, right? I'm gonna go ahead and do that. Do that. Okay, markdown. All right, so now let's start generating some random images. So remember, the only thing is these are not conditional. All right, so basically G model has been instantiated already. This is just random G vector input, so I believe this is just a vector of 100. So it should be this one, right? Random G vector input, so size 100. Okay. Then that generates an image. Let's actually break it down so that we can view it. So this should generate what? 1 by 784? Or 784, right? So we've got our image there. All right, now let's reshape it. Yeah, we're gonna print the shape. Dot shape. All right, 28 by 28. And then we're going to convert it, detach it from when it comes out of the torch, it's in the graph. So we have to detach it from the graph. And then we also we can convert it to NumPy and then just run it to matplotlib. That doesn't look so great. Let's try a few more, right? So maybe we did need 30 epochs. Okay. So that's not, but maybe it's just a random thing. So let's try a few more. I'm pretty sure this is from the MLP. Like these images, I did it with the MLP. Where's the core function? Yeah, generator net. So not generator DL net, right? Okay, so let's try another one. So these are all random. So if you notice, this is the same. So same. Yeah. Let's try a few more. Yeah, not so great, Joey.
Why?
That's all right. Try another one. That kind of looks like a 7, kind of. So as you can see, you do need a little bit more training, possibly. Yeah. So that kind of looks like a 6. So these are just basically random. Yeah. Got it? You guys get the idea, right? So possibly if we had given it the 30 at this, so go back to the original Jupyter and you can take a look. This one did about 30 or 29, and the images start to look a little bit better, I suppose. So in theory, if we gave it more, even more, they might be even better. I also tried, as I said, developing a deep neural network, which was this DLNet. But I remember running this and I just kind of like, it was taking too long and I couldn't quite get this one to work. So I leave this to you as an exercise to play with. Any questions? No questions? All right, so I'm gonna start this again, do the 30 runs. Let's take it's 6:15. Let's take a 10-minute break and then we'll meet back at 6:25. And then basically we're just gonna do the conditional part. I think there's still a few of you that are presenting today. Am I wrong about that? Or are there still a few people presenting today? I think there were. You are, yeah. All right, so yeah. Were you presenting? Yeah. Huh? Oh, already did. All right, yeah. So yeah, so okay, so not that many, and then we'll do conditional GANs basically. Okay, so I'll start this over here, and yeah, let's take a 10-minute break.